LLMs do not see text as sequence of words like we do. Rather, it sees a sequence of unique numerical IDs which are pre-assigned to every word present in the vocabulary. And this simple idea is called tokenization. Let's understand from an example. Suppose we have this sentence, the train arrived early. Now, how can we map this text into a sequence of numerical IDs so that model can understand it and also process and generate the output for it? Let's split this sentence into words and assign unique IDs to each of the words. Well, this is fine, but can you see the problem? Since we have to assign unique IDs to each word present in the training data, let's say this word arrived can have different forms as well, like arrive, arriving, etc. And similarly with the word early, it can have multiple derivatives like earlier, earliest, etc. And so in order for our LLM to understand each word, we'll have to assign unique IDs to each of the derivatives of these two words. And we have over 1 million words in the English language alone. So can you imagine how our vocabulary can explode if we keep on assigning unique IDs to each of the derived words of a base word? But why having a massive vocabulary is really a problem? Well, LLMs perform millions of calculations to generate its predictions. And if the vocabulary size explodes, then the number of calculations will go even higher, and which is not feasible. So now let's see how else we can convert our text into numerical representation. So instead of breaking our text into words, how about we split it into characters? While this may seem like a clever idea, and it can also bring down the size of the vocabulary to just the unique characters present in a language, the major problem is that the sequence length, which is basically the length of the sentence which we feed into the model to actually get the prediction, is not computationally feasible. And specifically, having a long sequence length directly impacts the attention calculation. We are going to talk about attention in this Transformer series. But coming back to tokenization, having a word-based tokenization or character-based tokenization, both are not feasible and best choices to make. So we need a tokenizer which keeps the vocab size in check and also does not lead to a very long sequence length. Which brings us to subword tokenizer. So in subword tokenizers, instead of breaking a word arbitrarily, we basically try to see which character pairs occur more frequently in the training data and try to merge them and assign a unique ID to them. This way, we can bring down the vocabulary size and at the same time learn some meaningful information from the text. Like characters I and G occur very frequently together, so they can be merged and assign a single token ID. And while there are many tokenizers available today, this is the key idea behind them. And we'll talk about one such tokenizer in great deal today, which is called Byte Pair Encoding. Hi, my name is Jyotsna and welcome to the Hidden Layers. I've created this channel to talk about the concepts of AI which I have learned in past 7 years, and if you're from software background looking to switch into AI roles and preparing for relevant interviews, or if you're just simply curious about how AI works under the hood, you're in the right place. So in this video we are going to talk about byte pair encodings in detail. And this tokenizer is used extensively in the frontier LLM models today, including OpenAI models. Along with that, it's one of the frequently asked questions in the interviews. So let's dive right into it. So let's understand how byte pair encoding algorithm works to convert text into sequence of subwords, which will be eventually converted into their numerical IDs. So the basic idea is, it starts with the most elementary form of text, which are characters, and start building upon it by learning which pair of characters to merge in order to learn a new kind of token. So the steps are something like, we start with individual character set and we add also the end of the word special kind of character. Then as next step, we count the frequency of occurrence of adjacent character pairs in the words across text. And then, as next step, we scan through this frequency pair map to find the most frequently occurring pair. Then, we join this pair to create a single merged token. And then we update our initial training data, which we had initially split by characters. So we scan through the training data again to see wherever this pair has occurred together, we join them to make a single merged token. And since by performing this exercise, we also found a pair which occurs very frequently in the data, We can also store this information in a list, something which we call as merged rules. Moreover, we also update our vocabulary to append this newly learned merged token. And that's all. Repeating these steps until we reach our desired vocabulary size is what gets us our tokenizer. So let's understand it from an example. We have a sample sentence here which we break down first into characters, and then we count the frequency of adjacent pairs of characters one by one. And can you see for yourself that how many times T and H have occurred together? So we have T and H occurring together 2 times in the first line in the word the, and even in second line in the word with and the, we have T and H occurring together, which makes the count of 4. And comparing with rest of the pairs, this was the most frequently occurred pair in this sample example. So following the algorithm we just discussed, we can merge all the instances of this character pair into a single merge token. And once we update our sentence, it looks something like this. All the characters are sitting individually, but the characters T and H are now combined together. So with this updated sentence, we again count the frequency occurrence of the adjacent pair of characters. And so this time, characters A and T have very frequently occurred together with a frequency of 4. So next we can merge these two. And now this time we have E followed by the end of character special token as the most frequently occurred token pair. So we merge them and update the training data. And as mentioned before, this process will be repeated until the desired vocabulary size is achieved. And so once the training process is completed, what we are left with is an updated vocabulary with a number of newly learned subword tokens. Along with that, we also have a list of merged rules which are applied sequentially in order to tokenize a new sentence. And so let's also quickly look at how we can tokenize a new sentence before we move on to the hands-on section. So first of all, just like the training process, we split our sentence into characters, and at the end of each word, we add a special end of the word token. This is crucial because it marks the word boundary. Next, we iterate through each word characters and we apply learned merge rules one by one to the word in order to tokenize it. We repeat this process for all the words in the sentence, and that's how we end up with tokenized subwords from a single sentence, which are then assigned their numerical mapping, and even this numerical mapping comes from the tokenizer. And now this is ready to be fed into the model. So, this was a step-by-step breakdown of the BP tokenizer algorithm. Now, I hope that you understood the algorithm. If not, please drop your questions in the comments. And now, let's build our own byte pair encoding model from scratch. So let's open Google Colab, and now I have already loaded a text file here with some random text, and I will also be sharing this notebook along with the text file through a GitHub link later in the description. So you can either follow along now or you can try this later. So first of all, let's just see the length of the document. So we have the data looking something like this. And now to create the tokenizer, the first step is to pre-process the data. So I'll just do a single pre-processing here, which is normalizing the data and basically converting it into lowercase so that we do not assign two different token IDs to the same word just in different cases. And now tokenizers such as BP requires an additional pre-tokenization step, which is basically splitting the text into words. And so let's just split the words. Okay, so we have around like 2.4k words, and also we need to split each word by the characters so that later on we can learn the merge rules and start merging the characters. So let's just name it initial corpus, which will represent our training data for the tokenizer. And here each word should be split by characters. So each word, this will basically split it into characters. And at the end of each word, we also need to add a special kind of token which will mark the end of a word. So adding to the list, just a special kind of token. And this token can be anything. You can also create your own special token to represent the end of the word. And let's just iterate over this in training words. Okay. Let's just check one of these. So the first word was foundations, which got split by the characters, and we have added this special token to mark the end of this word. So this whole thing was pre-tokenization. And now we create some helper methods which will be used while training the tokenizer. So first of all, we need a function which can calculate the frequency of the adjacent pairs. So let's just name it frequency pairs. And we are going to pass the corpus here, which is basically the list of list, which are basically nothing but the list of characters. And now for each word, we are going to find the pairs. So I can just initiate a dictionary for it. And let's iterate over each word in corpus. So now I am going to iterate over the characters of each word, and my plan is basically to count the frequency of each pair one by one. So this could be one pair FO, similarly OU, ND, and the last pair of this word would be this, right? So if I move my pointer from 0 through the characters, I should stop here, right? Because there's nothing beyond it. So basically I should move my pointer from 0 till last but 1. So which is what I can do. So I is less than length of the word minus 1 because I need to stop here. Now I can simply go through the word and update the dictionary. Frequency pair and word I. So this is going to be a tuple I plus 1, and we can first check if it already has the pair. Get, and let's just copy this. So if this pair does not exist in the dictionary yet, so it should be initialized with 0 counter and then plus 1. So this will count the frequency of each pair present in the words across this corpus, right? And that's it. We can just return this. Okay, I also forgot to increment the counter here. Okay. So now let's just check this frequency counter dictionary by calling the method, and we do this initial corpus. So now you see all these pairs basically have occurred across the words in the corpus, and this is what we are going to use to train our tokenizer model, which is to say that we are going to learn merge rules out of these. Let's just clear this for now. Another method which we are going to be utilizing is, once we have found our pair which can be merged, how can we update our corpus accordingly, right? So let's just create that method also, and the inputs which we are going to be expecting here are first the corpus and second that merged pair. Okay. So this is going to be a tuple with one pair of tokens, and each token could be one or more characters depending on if that token was created in a previous run by merging two characters. So first of all, we create the merged token out of the pair. So it's as simple as joining them. So 0th plus 1. So this gives our merged token. And what we are going to do now is we are going to recreate the corpus. The reason for that is we need to merge all the occurrences of this pair which are occurring together in our corpus across the words. So again, we are going to iterate first through words. Let's just initialize our new updated corpus, and we are going to now iterate over each word again, and each word now needs to be recreated because some of the characters may need to be merged based on this token. So new word, this is also going to be a list, and we will iterate over the tokens of this word. So the idea here is going to be, in each word, whenever we find this pair of tokens adjacent to each other, then we are going to merge it and then recreate the word. So suppose this was the word initially and we had this FO as our new merged token. So now the new word is going to be this FO is going to be a single entity in this list, followed by all the single occurring characters. So for that, while iterating through the word, we are going to be checking for the occurrence of this pair. If we found it, then we merge it and then we increment I by 2 because we do not want to again iterate through this as it's already merged and created as a one entity. And if we haven't found this pair, then we simply iterate through each character one by one and add it into our new word. So let's implement it. First of all, I am going to check for the pairs, and again while checking through the pairs, we need to stop here. So my condition is going to be if I is less than the last but 1 and this tuple word I plus 1 is equal to this merged pair tuple or not. If so, we add this new merged token into the new word dot append merge token, and then we increment I by 2 because we have already processed both these characters. If we haven't found this, then we simply add that character into the new word and we just move on. New word dot append and word I. That's all. And then once we're out of the loop, we just add this new word into the corpus. This new word. And once we are done, we just return this new corpus. And that's all. Okay, so now we can move ahead and create the training part of the tokenizer. This is going to be learning a list of merge rules. So before I forget, first of all, we need the vocabulary for our training data. And how we can create that? This was our training data, and this is going to be our initial vocabulary, and we can split our entire corpus into characters, which this would do, and then we create a set out of it, which will basically create a set of only unique characters, and we again convert it into list. So this is going to be our initial vocabulary. So let's now check the size of it. We have 33 characters in our vocabulary, and now in our training process we are going to learn some more tokens which will be added into the vocabulary, and I have this small snippet to do that. So let's just go through it together. First of all, I have initialized this training iteration, which is 500, and the expected vocab size, which is 1000. So whichever is reached first while training, either the training iteration is completed or the vocab size is already achieved, we will stop the training. And this merge rules is just a list which will be holding all the merge tokens learned in the order, and we will be using it to tokenize the unknown sentences which are not present in the training data, right? And now we have initialized our corpus with the initial training data which we had created, which looks like this list with characters. So here we start the iteration and go on until one of these conditions are not met, which is basically vocab size has either reached its goal or the training iteration is done. And we pass this corpus through this first helper function which we had created, and this is going to be providing us all the pairs frequency. Once we do that, this method provides us the pair with maximum occurrence. So we use this max function and we use the value, which is basically the frequency, to get the maximum out of this dictionary which we had created. And next, we are going to be using this update corpus method to join all the occurrences of the characters which we have found here as the most frequent one at this particular ith iteration, and so that the corpus can be updated with the merge token, which is what will be done here, and the corpus will be updated with this newly created corpus, so which is updated here. And now next we are going to add this merged pair into the merge rules, which is essentially the brain of the tokenizer, which is what is done here. And then we also add that merge token into the vocab and we just iterate over it. So now let's just run this. Perfect. So it has learned the merge rules. So say these two tokens got merged into one. And let's just now see the length of our vocabulary. Great. So we started from 33 vocabulary size and we have added 500 more to it. And this has now learned the rules which we can use to tokenize any sentence of our choice. So let's just try to tokenize an unknown sentence. And in order to do that, there's just one little more step left. So let's just go through this. So what we need to do is we need to run each word through all these 500 merge rules, and we need to check which of the rules apply to the characters present in the current word, and we need to apply them, so to say that we need to merge those characters in order. So suppose we had a word which had these two characters present, we need to first merge it and we again need to run that word through this second rule and so on, so that all the rules can be applied to that one single word. And this process we need to repeat for each word present in the sentence, which is what we are doing here. This tokenized word takes a single word into account. It basically first splits it into characters and then it adds that end token, which we had also done in the training scenario. Then we basically iterate that word through each of the pair in the merge rules, right? Which is what we are doing here. We create the merge token out of it and we iterate over this word's list of tokens one by one through each of the rules. So again we stop at the second last token and we check if this token pair is equal to this current merge rule pair or not. If so, we add the merge token and we skip the iteration by 2 steps. Or else we just add that token present at that ith pointer into the new token and increment by 1 and move on. So this way we apply all the 500 merged rules on each of the word to tokenize that particular word according to our newly created BPE model. And now suppose we have this sentence, we first split it into words and then we pass each word to this tokenized word in order to tokenize it. And so now let's just see this all tokens. So you see now how this is tokenized into subwords. So li came together, ts came together, and not is together, and so on. So this is a very simple way you can create your own byte pair encoding model from scratch, and it will be so useful if you also try to implement it yourself, because this is one of the most frequently asked questions in a lot of good companies. And that's all for today. This session was mainly focused on laying the foundation for tokenizers and discussing one of the popular tokenizer in detail. And in the next video, which will be coming up next week, we will discuss some more practical aspects of the tokenizer to develop an end-to-end understanding of the topic. So stay tuned. And if you have any queries or doubts, please drop it in the comment section. And if you found this video helpful, please show your support by liking the video. And I'll see you next week. Bye.